Hi, I want to discuss some interesting spaces that arise in applications that give nice applications of metric spaces, and that we will see also later in the class uh, as we go through some more involved topics. This might also serve to motivate your further study of metric spaces and give you some more examples to work with other than the ones like R, subsets of R, and Rn that we've mostly been focusing on lectures. Uh, and mostly the reason has been that those are much easier to describe, uh, and they don't have some of the issues that come with the abstraction. But the real reason why we're studying these concepts are so that we could ultimately discuss sequence and function spaces. So for those interested, I will now describe a little bit briefly a motivation, why you might look at these spaces, and what kind of metrics you consider on them, and then quick proofs of why these are actually metrics on the space. So in one of the lectures, we mentioned that ODEs can be thought of as an equation in F. And this means that we want to consider F as a variable. But to do that, we need the notion of F being in some space of objects. Now, there are also many other reasons why you might consider, we might want to talk about two functions being close to each other, say in the sense of approximation. So we have all seen these pictures of, say, sine being approximated by its Taylor series. And we want to say that these two things are somehow close to each other. And we don't want to say just that they are close to each other as pictures. We want to make this precise by giving a measurement how close. Now, depending on the application, we'll use different metrics. So an important aspect of infinite dimensional, especially function and sequence spaces, is that the same space can be equipped with different metrics that you might want to consider with different applications in mind. So I want to first start with the simplest metric on the space of functions. So the space of functions I denote by Bxr. Here, x is any set, and we consider all the functions from x to r so that these are bounded. So if we take the supremum of over all the elements in x of f of x, we insist that this is bounded number. This assumption is placed, and that's what the B stands for, because we need to ensure that this distance that we define is actually a finite number. So the distance, sometimes with a subscript infinity, but let's add that here, between two functions in this space is defined as we take the largest difference between these function values in our given set. So here we're looking at the differences between the graphs. It's worth mentioning that this function this makes usually sense only in a bounded set. You can talk about the convergence on all of R, but it behaves quite differently than just on some bounded subset of X. For example, Taylor series for sine would not converge with this metric on all of R because if you're far away, if X is very large, then the difference between the Taylor series and the function itself would be quite large. So usually we restrict to some bounded subset. And first, let's connect it to this assumption. Well, d infinity fg is equal to supremum over all points of fx minus g of x. Well, the absolute value is less than or equal to the sum of the absolute values by triangle inequality. So supremum over x of f, absolute value of f of x plus g of x. Now this is a sum of two things. They may not attain their maximum at the same point, so this is usually a strict less than or equal to. But the maximum, by simple, an upper bound for this thing is if we first maximize f and then separately maximize g. First maximize f and then separately maximize g. And this might be strictly bigger than the supremum of the sum. It's not always equal. But this is a sum of two finite numbers, so this is less than infinity for all f, g in this space xr. So this ensures that the metric here is actually defined. Now, to connect this with a small remark, to connect this with the lectures, a supplementary lecture on inequalities and norms, what we really have done here is define a distance based on a norm. So the norm of f is supremum over x in x of absolute value of f of x, and the distance between two ones is equal to the norm of the difference. So that's worthwhile to notice, and that also comes up a lot in the proofs. Now, some of these properties, so this is a metric. We want to show that actually this satisfies the axioms of being a metric. As usual, some of these properties are quite simple. Well, if we have for all x in x that the absolute value of the difference is non-negative, so supremum of these numbers is also non-negative, and this is the distance, infinity distance between f and g. So that's the case there. If you wanted to expand this out, you would start from the assumption, suppose f and g are functions, then this would be whole. Now, symmetry, well, up to the f of x minus g of x for all x is equal to g of x minus f of x. Therefore, if we take the supremum of these both, this function on the left and this function on the right, we get the same thing because these are identically equal. But this one is the distance from g to f, verbatim. And here it's important, why we write it this way is that in the definition, the function that syntactically comes first is the function that also comes first in the difference. Of course, we know that that doesn't really matter, and that's what this proof is telling us. Now, 0 is a little bit trickier. Well, but not very much. If distance fg is equal to 0, then what do we get? We get that supremum x and x of the difference between fx and gx is equal to 0. This tells us that if I take a particular value in x, then the difference between f of x and g of x is less than the supremum, which is equal to 0, and it's a non-negative number because it's an absolute value. So therefore, we get that for all x, absolute value of fx minus gx is equal to 0. So for all x in x, fx is equal to g of x, which means that f is equal to g. Two functions are equal if their values everywhere are equal. Triangle inequality. This one, it's fairly intuitive, but one has to be a little bit careful about the quantifiers here. So let's write this a little bit out more carefully. Fix f, g, and h functions in Bxr. Let's look at the distance in infinity between f and h. Well, let's actually before that, because we we want to say first something that's true for all x. So for all x, it's true that if I take the difference in the function values of f and h, this is less than or equal to the difference between f gx, the usual triangle inequality, plus gx and minus hx. I mean, this is the heart of the argument. Now, the right-hand side here, since supremum is an upper bound, is less than if I first bound the first term from above by supremum over x, f of x minus g of x. And then the second term is bound from above again by the supremum over x of g minus h. And I'll just leave the x's there. Now, a small thing here is that this is technically an abuse of notation, because in the supremum, this is a dummy variable. And on the left-hand side, this is free. So there's a conflict in the role of y's and x's on both sides. If you wanted, you could be very careful here and put a new variable here, y. This way it wouldn't happen. But by allowing this small ambiguity and without introducing this artificial new variable, we write this and we understand that the x on the left-hand side and the right-hand side are not quite the same. So occasionally we will simplify things a little bit like this. Now, the right-hand side is a value that does not depend on the free variable x here. Actually, let's put the y here just because otherwise we're saying silly things here. Because of course it depends on x, but x is in a different role. So f of y, gy. So the right-hand side does not depend on x. So it is an upper bound. For fx minus h of x for all x, or the set of values fx minus h of x absolute value. So if we take the supremum of this set, it is the least upper bound, and therefore it's less than that. And this is where we also add the definition. So the first one here is d infinity fg plus d infinity gh, and the left-hand side now became d infinity fh, and this is exactly what we wanted to show. So the main thing here is that we are clear about when we are taking the supremums and in what order. This is usually what happens in the supremum proof. So now there are many other metrics. On infinite dimensions, you actually always have different metrics that you can use. And the most important ones for applications are the so-called integral metrics. And these only make sense if you make some stronger assumption on the function. And this is because they involve an integral, and we have to ensure that the integral exists. So let's C01 be the set of continuous functions, say, on R, on 01. And if we have such continuous functions, then you could do any other closed interval, but 01 is a common one to write this out. Then we define the distance as, actually, let's write it for a general interval because the way we highlight it works for all. So the p distance between f and g is the integral of, we look at the difference fx, f minus g, we raise that to the power p, and then we take 1 over p, and this is integrated on the domain of the function, dt. And again, there's a norm that this comes from. Norm of f with respect to p is the distance to 0. So integral from a to b f to the power p 1 over p. So this is just the distance associated to that norm. The norm of f minus g. Now, again, because this is built from the absolute values, it involves the differences. The positivity, symmetry, and zero properties are the easiest to prove. The zero property is a little subtle and actually involves this continuity. So for the zero, you can prove that, well, absolute value of f to the p is continuous. That if you have a function h that is continuous, on the interval a, b, and integral from a to b of h to the p is equal to 0, then h is actually equal to 0. But this crucially uses continuity. So this is a good exercise to test your understanding of integrals, but I won't do it now because it's really a topic of 131a. But triangle inequality is the main one that is interesting here. And I'll just discuss the p equals 2 case because it's considerably easier than the other cases. The other values of p involve looking at the so-called generalized Minkowski-K inequalities. But let's look at integral from f minus g. Well, by the usual trickery with norms, what we need to prove that the norm f plus g is less than the norm of f plus the norm of g. Okay. So we have f minus f plus g squared. And this can be expanded as integral over ab f plus g times absolute value of f plus absolute value of g. That's our first step. And then looking at the right-hand side, this can be estimated from above by first distributing, estimating the first term from above by Holder. This gives integral from a to b, f plus g squared, square root, and then integral from a to b, f squared, square root, and then the same, but with g, replacing the second factor. And then I'll mention what Holder is in a second in this form. Now what we have is we have this term, it's dividing both factors and it's on the left-hand side. So we divide by the blue factor and assume that it's not 0. If it is equal to 0, that means that the left-hand side here is equal to 0 and it's trivial, because the right-hand side is always non-negative. So we can divide by the blue, and what we get is on the left-hand side, integral a to b f plus g squared is less than the square root of integral a to b f squared plus square root integral a b g squared. This will be done. Now what we used here, it was Holder's inequality that in this case can be written as integral from a to b of fg is less than the square root integral from a to b f squared times square root integral from a to b g squared. This is something that's a nice exercise to prove. And the hint for this is to proceed just like you did when proceeds in the single variable case. So you look at integral from, you look at the function f of t is equal to integral from a to b of f minus tg squared. And this is we integrate in x. You expand f and minimize in t. And what we have is that this is always non-negative, and the minimization in t then leads to that inequality. So this is the special case of the D2 distance on this space that's particularly important for applications such as probability analytic effects. So there's an example of how these metrics are different. Now, if I had the sequence of functions, say, we have the space x is equal to 0, 1, and fn of x is equal to 0 on most of the space, but then from the interval 1 minus 1 over n, it quickly grows to being 1. Now, limit as n goes to infinity, f of n of x is equal to the 0 function. So 0 here is the function that's always equal to 0. So 0 of x is just equal to 0, 0. But in what distance? Well, in some sense, in the D1 metric. Why? Well, let's look at distance D1 fn minus 0, fn 0. This is equal to the integral of absolute value of fn minus 0. And this here is just absolute value of fn, which is positive, so we have just integral of fnx. Now, what is the integral of fnx? It's just the area of this triangle. This could be proven rigorously. So the 1/2 the base times the height, and this goes to 0 as n goes to infinity. So therefore, fn converges to 0 in this metric. But limit n goes to infinity of fn of x is not equal to the 0 function in the infinity metric. Why? Well, if we look at fn of x minus 0, absolute value, and supremum over all the x in 0, 1, well, what is the largest difference between this function and 0? It's attained at this endpoint where we have a difference of equal 1. So this is an upper bound for the set, and it is attained. So the supremum is equal to the maximum, which in this case is equal to 1 for all n. And this means that the distance infinity of fn to 0 is always equal to 1, and limit as n goes to infinity, the infinity fn to 0 is equal to 1, which is not equal to 0. So fn does not converge to 0. A very important example. So these metrics are resolving some different details. The D1 metric sees the fact that this area here is very small, so the graphs are very close in area, whereas the infinity metric insists on the graphs actually being very close. So this gets at the idea that functions and things can be close in different ways. And this is particularly important for another application in a more discrete world, namely data analysis. In data analysis, we have some sequences of values, and these might be real numbers. Could be a time series analysis of, say, a stock price. And we'll denote this by, so xn is some sort of, it could be the measurement of some data, say. So data at time, usually somehow normalized, n delta t, because we have discretized also time. And there's some initial time, t naught, that we have started sampling from. And we could ask, how similar are these sequences to each other? Now, and another thing is that often in algorithms, we will somehow start from removing error from the data, or we will simplifying the sequence. And this leads to a low dimensional approximation, and we want somehow in that this transformation that simplifies our calculation ensures some sort of closeness of this approximating to the full thing. So this is like a function to its Taylor series. Now, we imagine either having a very large sample size or even mathematically infinite. So for the infinite case, we have an infinite sequence of numbers that come from conducting, say, measurements. And we can define different spaces from them. The L infinity space consists of all sequences such that the supremum of its components are bounded. So supremum I equals in n of x n I is less than infinity. And this is denoted, we note a sequence by listing its elements, or we could give a formula for its elements. So these are two ways of describing a sequence. But just like for functions, we can look at different ways that the sequence might be finite, and another way to look at involves a pth sum. And these are roughly, for the same reason, important as these are for function spaces important. In fact, function spaces sometimes can be represented by sequence spaces. For example, if you know about a Fourier series, then a certain function space is equivalent to a certain sequence space, and this plays an important role. So for sequences, we can define the infinity distance between two sequences xn and yn by looking at the largest difference in their components. Or because this is an infinite set, we cannot look at the largest one, but we have to write the supremum. Now, similar to before, one can prove all these properties that we had before, and the only one that's non-trivial is triangle inequality. And for this one, it's crucial to again start from, for all I natural numbers, what we have is that x and I minus z and I is less than x and I minus y and I plus y and I minus z and I. So for the real numbers, now this is less than its upper bound, which least upper bound, which is d infinity x to y plus d infinity y to z. And now taking the sup on the left-hand side, for this is another way of saying that this is an upper bound for the left-hand side, so it's enough. It becomes an upper bound for the sup. So what we get is that distance infinity x to z between these two sequences, which is the supremum over natural numbers, or the difference in the components, is bounded from above by the distance between x to y plus the distance between y to z. So it's the same proof as before. And you could do the same thing for LP distances. So as before, so we define distance p distance. This is defined for p between 1 and infinity. As the sum, we look at the differences in the components, x and I minus y and I goes from 1 to infinity, and we raise that to the power p, and then take 1 over p on the outside. Now this is a metric, and this can be proven by applying approximation. As follows. So for all capital N natural numbers, we have, by the finite dimensional of Minkowski inequality, that sum I equals 1 through capital N of x and I minus z and I to the p 1 over p is at most I equals 1 to n x and I minus y and I to the power p 1 over p plus sum equals I 1 through n y and I minus z and I to the power p and 1 over p. I'll write that again just so you can see that a little bit better. So plus I equals 1 through n y and I minus z and I to the power p 1 over p. So why I write this way is that we had proven that this claim holds in finite dimensional space if we take finitely many of these components. This is often the case when arguing about sequences. Now, there is usually a trick of approximating from above one side and then taking a sequence, a limit as n goes to infinity. This is analogous to what we did here, is that you can approximate one side from above and then after that take a supremum. So on the right-hand side, the limit I1 goes to n, x and I minus y and I to the p 1 over p. This is always less than or equal to if we take the sum up to infinity. And similarly for the other term. Why? Because x and I minus y and I are all with non-negative real numbers for all our natural numbers. So here we're summing up more numbers. And it is possible indeed, and the issue why we have to be careful here is it's possible for these sums to be infinity. They won't be in these applications, but they could be infinity. And that's why we have to be careful. But this is a finite number. It certainly is less than an infinity number if that were the case. So that's not really a problematic case. And that, therefore, this reasoning is perfectly sound. So that is less than the infinity sum. So what we get from this is that for every natural number, capital N, if we take the sum on the left-hand side up to n, and we keep the n there, then what we get on the right-hand side is the dp distance, x to y, plus the dp distance, y to z. And here we should have x and I, z and I. But this is now true for all n. So the right-hand side is an upper bound for the left. So what we get is, and by sending n into infinity, well, or rather, yeah, again, this series is a sum of positive terms. It's bounded from above by this quantity, and therefore it converges. And then we send the limit, take the limit as n goes to infinity, and what we get is sum I equals 1 to infinity of x and I minus z and I, which is distance p x to z, we have to have the powers p here, is less than or equal to dp xy plus dp yz. Remark, we should also check that dp of xy is less than infinity for x and y in this LP space. But by same argument, we get that dp of x0, dp of xy can be bounded from above by dp of x0 plus dp of y0, and these are finite because x and y are in LP. Okay. So that's a lot of very technical proof, but again, the important thing here is, on the one hand, knowing these techniques that you can apply these Hölder's inequalities, and you can apply these limiting arguments to get these metric properties. That's one part. But another part is to get a sense of what this convergence means. And for that, the best thing is to do is just look at sequences and seeing whether they converge or not. So let's start with a sequence xn. This is a sequence of sequences. So each of these elements could be different. And what we define is xni equals 1 over n for for the first n indices. And then after that, we define it as equal to 0. Now, a short lemma, that if we look at the L infinity distance, then the xn converges to the 0 sequence. However, if we look at the L1 distance, then it doesn't converge. Notice how this is completely opposite from what happened in the function spaces. There we had a sequence that converged in L1, but didn't converge in L infinity. So this is a different direction. So finite discrete, this sequence space somehow behaves differently from the function space. And this is a source of many important examples in other areas of that. But okay, we want to show that it converges to 0. Let's look at the d infinity distance of xn and 0. Let's call this a and b. So d infinity x to 0. Well, this is supremum over I of x and I minus 0, which is just because x and I are non-negative, is the largest component of x and I, which is equal to 1 over n, because there are only two possible components, 1 over n and 0. Equals 1 over n, or x and I is equal to 0 for all I and n. So we get the supremum is 1 over n, and therefore limit as n goes to infinity of the distance between the sequence xn to the 0 sequence is equal to the limit as n goes to infinity of 1 over n, and this we know to be equal to 0. We're done. By definition, if the distance converges to 0, the sequence converges. So limit as n goes to infinity of xn is equal to the 0 sequence. B, though, let's look at d1 of xn to 0. Now this is the sum of the components between xn and the 0 sequence. So xn I and 0, I equals 1 to infinity. Now, by the definition of x and I, this is the same thing as if we just sum up to the nth index of 1 over n, because after that, the distinct indexes are the same. Now we have n terms of size 1 over n, so we get 1. Again, d1 of xn 0 is equal to 1 for all n, natural. So limit as n goes to infinity of the distance, it does converge, but it converges to 1, which is not equal to 0. So xn does not converge to 0 because limits are unique. We're done. In fact, you could prove more that xn doesn't converge at all, doesn't converge to anything. But this needs the idea of a Cauchy sequence. This requires showing that xn is not Cauchy. And for more discussion on that, see the videos of this week. Now, what I will end with is just a nice further example that I won't fully prove. In abstract computer science, in logic, it's very useful to look at a different, much more combinatorial type metric. This comes up also in probability, and it's a question about how similar are two words. Now, words are sequences of elements. For example, A, P, P, L, E would be a word in the English language. We have a set of letters that depends on the language that we use, or it could be characters depending on the language. And, well, words end at some point, so we do have to allow a blank character. So I will just denote it by a bracket, or yeah, so every word actually in our case ends with an infinite sequence of brackets. And then we have a space of all words. Now this means space of all possible words, or it could be the space of all words. You could restrict it to the space of all words in a given language. And there is a neat metric to define by taking 2 to the power of minus the first index where these words are different. So for example, and this is better understood through applications. So take the word apple, this is word, and after that you have blanks, but I don't write them. And the word application. And the blanks are important because these words have different length, but you compare the characters depending on where the first, yeah. So these first 4 letters of these are the same, but I is different from E, and that is the 1, 2, 3, 4, 5th character, so 2 to the minus 5. Another example, story and silence, they already are different in the 2nd character, so the distance is 2 to the minus 2. Now one can show that this is actually a distance. Well, it's kind of obvious that it's non-negative because you take 2 to the some power. One should add a special case. Distance word to itself is always equal to 0. But if you have different words, they eventually are different in some index, so you do get something positive. The way this is phrased is evidently symmetric. So the only case that you really need to check is the triangle inequality. And you can actually prove a stronger form of the triangle inequality, namely that for every 3 words, the distance from x to z is at most the maximum of the distance x to y, and the distance from y to z. And as a hint to how to prove this, if you know that the words x and z agree up to the kth index, that means up to k minus 1 really, then you know that xk is not equal to zk. But if xk is not equal to zk, y cannot agree with both xk and zk, because if it agreed with both, then, well, x and zk would also agree. So that means that y has to be different from one of these numbers in the kth index, and that means that the right-hand side one of these terms has to also be bigger. There's some case checking and looking at the definition, but it's a nice application. This property is, by the way, called being an ultrametric, and you can read many other places about these, and these are sources of many interesting examples. So thank you for listening. Hope you have found this interesting.